Our video on relativistic momentum is going to be a short one. We're not going to spend very much time talking about momentum, but we will see it again when we talk about energy. So when we look at this, we look at the equation for momentum. It should look very, very familiar. Momentum in the classical sense, in classical physics, is mass times velocity. Here we see that we have this Lorentz factor right here. So it is going to be momentum is equal to mass times the velocity. Notice we've used U now. U is typically for velocity in a different frame of reference. I guess the frame of reference here would be the frame of reference of the object moving. But we have mu instead of mv. No difference there. The difference is this Lorentz factor right here, gamma, where basically as we get closer and closer to the speed of light, as u approaches c, gamma becomes larger and larger. So in any case, we want to take a look at this, but I do want to point out something. Some approaches for relativity, for special relativity, treat mass as if it actually changes as we go faster and faster. They'll say there's a rest mass, which is the mass of something in a frame of reference when it's not moving, but as it goes faster, the relativistic mass is gamma times m. I think that is not entirely correct. It does help students visualize a little bit about how momentum is getting bigger. I think it's more correct to think about the mass as being invariant, that there's no relativistic mass, mass is mass, and that when we look at momentum, it is the momentum which is changing, not linearly proportional with velocity, but also dependent on this Lorentz factor. So I don't know, some instructors like to teach that there is such thing as relativistic mass. I think that causes all kinds of problems because, of course, mass creates gravitational fields, and I don't think that translates so well when you try to use that idea. In any case, let's take a look and see what happens as a function of velocity. If momentum were just simply proportional to velocity, we would have a nice straight line, and the slope of that line would, for momentum as a function of speed, would just be your mass, your inertia. But here you can clearly see it does sort of start out as a straight line, although that's difficult to see here, but then it starts curving upward. And as we approach the speed of light, this value for momentum keeps going higher and higher asymptotically. So what's going on here? Well, think about Newton's second law. Newton's second law states that the net force in an object is equal to the change in momentum over time, or the derivative of momentum over time, the rate at which momentum changes as a function of time. So let's say that you're at some high velocity, nearly the speed of light with a very, very large momentum. Any small bit that you want to go faster by Newton's law would require a large force over a longer period of time. Now, as this gets steeper and steeper and steeper, the slope becomes greater and greater and greater. The amount of increase in momentum that you get for a given amount of force for over time, a given amount of impulse, is just getting larger and larger and larger until finally, as we approach the speed of light, the force required to add any additional impulse goes to infinity, or the time required for any given impulse to increase the momentum would go to infinity. So basically, we can see why there is this speed limit, at least for objects with mass. It would require an infinite amount of impulse to reach the speed of light, okay? And obviously, if you want to do this in terms of work, we'll talk about energy a little bit later, it would require an infinite force. It would require an infinite amount of energy. So really, we're stuck if we have mass, if we have inertia, we're never going to reach the speed of light because of this relativistic momentum. So there's your barrier right there. Can't pass that. 1 times c. And again, this leads to our ban of anything with mass traveling at the speed of light. Of course, we know that light travels at the speed of light. That's sort of redundant to say that, but light cannot have mass. Therefore, it's able to travel to the speed of light, or really, I should say, the fact that the fact that gravitational waves do not carry mass with them allows them to travel at the speed of light. Can't go past c. That's your speed limit. Again, you can go 0.9999. You can put as many nines as you want there, times c as possible. But you're never going to reach c, with mass. It's just not going to happen. So let's do a relativistic calculation. This is okay. This is not an electron being accelerated to any ridiculous amount of energy. This is an electron probably being accelerated. You could probably get accelerated in a cathode ray tube, pretty comparable in terms of velocity. But we're going to take a look at momentum. The mass of the electron, very, very light, 9.11 times 10 to the negative 31 kilograms. We're going to just get it to go 98.5 times the percent of the speed of light. We calculate gamma for that, and we get 5.80. So 5.80 basically tells you how much this relativistic momentum is going to deviate from the classical momentum. So P equals gamma mu, u is basically V. 5.80 times our mass, okay, times, notice I put 0.985, and then I put the speed of light. That's just an easy way of putting the velocity in that equation. So what do I get? I get a momentum of 1.56 times 10 to the minus 21 kilograms meters per second. Nothing crazy about that. Very similar to the momentum calculations we've done previously. The big difference, the Lorentz factor there. Now, let's do something fun. Consider a baseball. Baseball is a bit heavier than an electron. 0.145 kilograms, 145 grams. And we're going to fire this baseball at different values or fractional values of C. Obviously, we can't go up to 1, but we're going to try to get a little bit close to 1. So pitching a fastball, that'd be about 45 meters per second. In terms of the fraction of the speed of light, it wouldn't register. Gamma would basically be 1. Not surprising, because we're really in the realm of classical physics. Classical physics works fine here. And we get 6.5 kilograms meters per second. That is our 100 mile per hour fastball. Now, if we go to, let's say, 1/3% of the speed of light, not 1/3 of the speed of light, but 1/3% of the speed of light, again, we're still pretty much in the classical range. When I calculate gamma here, I don't deviate very far from 1. Still, I have a huge momentum at that velocity, be about the same as a medium-sized truck going 100 miles per hour, getting hit by something going that fast. Okay, let's think about that. 1 million meters per second. 1 million meters per second, and that's 2 million miles per hour. Don't have too many things comparable in the macroscopic world that go exactly that fast. When you think about something going in orbit around the Earth, I think we're probably around 10 to the 4 meters per second. So this is going 100 times faster, but still not really in the relativistic range. Okay. Up to, let's jump here. 1% of the speed of light. Still not very different. We still get a good approximation in the classical calculation. P equals mv, P equals gamma mu. They're going to give you the same thing. At 3.333% the speed of light, Now we're talking about the momentum of a locomotive engine going 80 miles per hour. Still not really very relativistic of a calculation. Okay, correction. 10% of the speed of light, still less than 0.5% difference between the classical calculation and the relativistic calculation. Here, now we're at a third of the speed of light. And we get a 6% correction, meaning that if I calculated this classically, I would be around 6% too low in my calculation. So the errors are becoming significant. We're deviating in this relativistic realm. Half the speed of light, now it's significant 15% difference between our classical measurement and our relativistic measurement. That's about the same momentum of 747 at cruising speed. Going up to, let's jump here. Let's get to a Boeing 747 at 96.7% of the speed of light. Now it's, it's certainly relativistic because we're getting nearly 4 times as much momentum out of our relativistic equation versus our classical equation. Getting hit by that baseball is not only going to have the same momentum as a 747, it's also going to concentrate the energy in a very, very small area. Apollo 11 in Earth orbit would be that baseball traveling at 99.67% of the speed of light with a Lorentz factor of 12.3. And of course, you can see so on. But again, it really shows us where relativity becomes significant. Right between 10-20% of the speed of light, you're starting to get a significant correction, at least in your momentum calculations. So, that's where, you can still get a good approximation with our classical equations, but, those corrections are becoming significant now.